Cut your engine, mate, or I'll stop the video there. Okay, so this is your Year 12 Specialist Maths folio task, and what's good about this is that it's a very open-ended problem, and says froth over open-ended problem tasks, and what that means is you don't have an answer. We're not looking for you to get the answer and everyone sort of gets the same answer like you will in a test. We're looking for you to perform an investigation, which is why you get to choose the numbers, not me. So I want you to have a bit of a read through. I'm just going to go through some of the opening problems that you'll be dealing with you, so you can show those skills and so forth. So we have two mosquitoes in space. For now, I'm just going to define one mosquito so that we can just illustrate the calculations with one mosquito. So let's say we have mosquito A, and I'll just pick some random numbers. It has a position of 696. All right. Now it's traveling towards a human being. This is where it is at time is 0. It's traveling towards a human being. Let's call them Pascal, who is located at
1, 2, 3.
1, 2, 3. Right. So they're quite close. Where distances are in centimetres, they're reasonably close to each other.
So it's quite close. Yeah.
Okay. So let's have a look. Part 1, for some sensibly chosen values, so we can adjust these accordingly. Find the parametric equations for the position of each mosquito at time t, where t is time in seconds using centimetres for different distance, and what is the speed of the mosquito. Okay, so we have a mosquito here, and it's travelling towards Pascal. So you can think of it as like, it's at, let's call it Pascal, so I can have A and B. We have a mosquito at A and it's travelling towards coordinate B, and so the direction that the mosquito is driving in then, that is flying in, is vector AB. So if we want to calculate the vector from A to B, it's going to be 3 take away 6, all right, 2 take away 9.
You're doing it in the wrong order.
From A to B, B take away A.
You're doing the Z's first.
At least the middle one's right. And 1 take away 6 will be -5. All right.
After you first, that is.
So that's the direction that the mosquito's heading in. Now, so if we're going to describe the path of the mosquito, we would just say, here's its initial position. So the mosquito A's line, the line that it travels is 696, plus some parameter, t for time in seconds, and then this is the direction in which it's headed, -5, -7, -3. Okay, now if we were to do that, who can tell me, just based off this equation that we've constructed, how long will it take to reach coordinate B?
1 second.
Oh, genius, you did that so quickly in your head. Of course that's going to be true because we've dictated it's travelling that whole vector in, that's the magnitude of that whole vector in 1 second. So we're going to need to adjust it a little bit, okay? So at the moment it's going to take 1 second to travel that distance. And so one thing we should do is sort of break it down and work out, well, how far is it travelling and how far do mosquitoes travel? So if we want to work out the distance from A to B, that's going to be the modulus of vector AB, right? That's the square root of 5 squared plus 7 squared plus 3 squared. So what do we got there? 25, 49, and 9. So who wants to evaluate this for me to 3 6? We'll have 74, 83.
Yeah,
Square root of 83 will be just over 9. So 9 point something.
9.11.
Excellent, okay. So, we've set up this scenario where the mosquito's already 9.1 centimetres from the person's nose. Okay, so this is going to give you a bit of information on how to adjust your numbers, right? You're seeing me just make them up. I'm going to perform the mathematics, but you're going to try and construct the numbers so that we have a realistic scenario, okay? So 9.1, not kilometres, centimetres. Okay, then we can look up how fast does a mosquito fly. I reckon from historical folios, some students found about 50 centimetres a second. Okay, so we can take that into account regarding our speed and so forth. Let's say for now, for our argument, that mosquitoes travel at 3 centimeters per second. So let's say we want it to travel at 3 centimeters per second. All right. And so it has to travel 9.1 centimeters. That's the magnitude, right? That's how far it needs to travel. So here's what we can do. We can convert this to a unit vector. Okay, if I'm at 696, this is its coordinate, here's time, and the unit vector is this whole vector divided by the modulus of the vector, right? Root 83 minus 7 root 83 minus 3 root 83. Now what that means, because we've converted it to a unit vector, is that this vector is 1 centimeter long. Okay? So if we want this vector then to have a length of 3 centimeters, we're going to be multiplying it by, at the moment it's 1 centimeter, if we want it to be 3 centimeters, we would multiply it by 3. So therefore, for mosquito A, so mosquito A's path, such that velocity, the modulus of its speed is 3 centimeters per second, is going to be 696 initial position plus the parameter time multiplied by, and then multiplying all those by 3. Okay, so we dictated a speed there rather than calculated the speed. Okay, what is the speed of each mosquito? How long does it take to reach the person? Okay, given that it moves at 3 centimeters a second and the person is 9.1 centimeters away, you can do a speed, distance, time. Okay, speed, which one goes at the top? Speed is distance on time, isn't it? So we want to know the time. Time is distance on speed, so we'll have 9.1 divided by 3. We'll have 3.3 seconds for the mosquito to reach the person based on this circumstance. Okay.
Miss Drexel would hate you right now. Speed is S and distance is D.
That's disgraceful.
That is disgraceful.
We're coming here, it just...
Hey, they're scalers, alright? Alright, so that's sort of part one. I've done it for one mosquito, you'll be doing it for 2 mosquitoes. Okay. Now, I'm gonna just invent a new mosquito path for now. You're gonna come up with them, but I'm just gonna invent it for now. Because what we have is we have another mosquito traveling through space. Let's call it mosquito B. And its initial position, we'll say -2, 3, and then -15. It's quite out there on the z-axis. And it also has the parameter t. Why? Because its position is dependent upon time. Okay? And let's just make up a direction vector as well. 1, 1, 2. Alright. So that's mosquito B. We have mosquito A and mosquito B. I'm just going to change it to P because we've already found vector A, B, and so forth. Mosquito P. Now, one thing we can do is we can find the distance between mosquito A and mosquito P. Alright, because what we have here, and what you'll be learning about next week, is we have what are called skew lines. Just look for something, maybe a text there. Okay, so if you think about, we've done a fair bit of lines in 2 dimensions. And when we have lines in 2 dimensions, we have 3 circumstances. Either the lines are parallel, which means there's no solutions, they're never going to intersect. Either they intersect, in which case there is one solution, or they're coincident, which means they're the same line. They're the 3 circumstances you have for lines in 2 dimensions. Now you're going to learn about that in 6G.1. The whole exercise is dedicated to that. In 6G.2 and in 6G.3, we have lines in 3 dimensions. So let's, based off of what we've seen here, how could you possibly have 2 lines in 3 dimensions interacting? What could they be? Let's hear some words. 2 lines in 3 dimensions.
Orthogonal.
They could be perpendicular, yep. So in which case, you could have 2 lines in 3-dimensional space that intersect. Okay, so you can still have intersection. Can you have parallel lines? Yep. Can you have coincident lines? There's one more.
They don't touch.
Excellent. When they're skewed, okay? They're skewed, that means they don't touch. And so that's what the parts of these mosquitoes are going to be. The mosquitoes aren't going to collide into one another, they're going to be skew lines. And so that means one's shooting up that way, one's shooting up that way. They never touch, but there is a point in time when they are closest together. All right? And so in 6G.3, when you watch that video next week, we'll be going through how to find the shortest distance between skew lines. And so what we'd be doing, if I find vector AP, that's the vector between mosquito A and mosquito P, I can work out the modulus of this vector, okay? And the modulus of this vector is going to be some equation involving T. It's going to be some equation involving the parameter T, and we want to know what's the value of T such that the modulus is minimized. When are they closest together? And then we can find their positions. All right. Do you want me to go through that or leave it for now?
Sure, why not?
Sure. All right. So here's exactly what I mean. And I'm just going to make it, when I perform it, I'm going to use these numbers just because they're a little bit simpler than those numbers there. Okay, so if I'm going to find the vector from A to P, vector AP, okay, this is the vector that exists between mosquito A and mosquito P. All right, it's going to be the x value of P, take away the x value of A. All right, so I might write it in parametric form for us. The x value is going to be -2 plus t. So that's the x value of P. Take away the x value of A, 6, take 5t. Okay, and that's going to be our x value dependent upon time. We can do the same for our y value. So we've got 3 plus t for line mosquito P, and 9 take 7t for y, and then for z. All right, I'll do it. Let's do it quickly. What do we have? -15 plus 2t. Take away, and then 6 take 3t. Okay, let's simplify these. So we'll have -2 take 6. That's going to be -8. And 1 take away -5, 1 plus 5, 6. For y, 3 take 9, 1 plus 7, and for z, -21 and 5. Okay, so what that means is this describes the vector between mosquito A and mosquito P for any value of time. And so if I want to know what's the distance between mosquito A and mosquito P for any value of time, it's the modulus of this vector, right? So that's the square root of 8 plus 6t squared, and then the y component, and then the z component. Now, we can't simplify that. Okay, I mean, we can expand it and collect like terms, but what are we going to have in this square root? What kind of equation are we going to have?
Linear. Wait, quadratic.
Quadratic. There's going to be
Not
some
linear.
quadratic in here. Ax squared plus bx plus c. Positive a value, which means we have a minimum. If I graph this, what have I graphed? It's the modulus, the distance between the two mosquitoes with regards to time. And so then this point here is when the distance between them is minimized. That's when they are closest together. Very good. All right, so that's sort of part 2 and beginning to look at part 3. But I think that's enough for us to get started. Any questions from you guys at this stage?